Special relativity. Light wave faster than the speed of light. A ray of light is emitted at time t prime equals 0. A receiver is placed at x prime b equals negative 100 c relative to k prime. Observer k prime is moving at speed 0.8 c relative to observer k. At what time does the ray reach the receiver relative to k prime? The wave reaches the receiver at time t prime b equals negative x prime b over c equals 100 seconds. The reason why the relation has negative sign is that because we are assuming that the time is measured from 0 onward as positive value in frame k prime. We compute the Lorentz factor gamma equals 1 over the square root of 1 minus v square over c square equals 1 over 0.6. Relative to k prime, point B has the coordinate x prime b equals negative 100 c meters, and the time at which the wave reached the receiver is t prime b equals 100 seconds. To find the corresponding coordinates of point B relative to observed k, we have to use the spacetime transformation at point B. Substituting the coordinates of point B and the spacetime transformation, we obtain the light wave reaches observer k at coordinate xb equals negative 33.33 times c meters. The light wave reaches observer k at time tb equals 33.33 seconds. Notice also that if we divide tb over xb, we obtain tb over xb equals negative 1 over c, or tb equals negative xb over c. What is the length of r prime as measured by k at the same time? To find the length of r prime relative to k, we have to find its coordinates at the same time. R prime as measured by frame k equals xb minus xo prime. We can find xo prime by substituting x prime, o prime, equals 0 in the spacetime transformation. At time tb, the coordinates of point O prime relative to k will be the following. By dividing xo prime over tb, we obtain xo prime equals v time tb. The coordinate xb as measured by k is xb equals negative c times tb. The length of R prime relative to k will be R prime as measured by frame k equals xb minus xo prime equals negative t times the speed c plus v. We have seen in task 1 that the radius of the wave has the term c minus v, which is the speed of light minus the speed of the frame. We see in the current task that the radius of the wave has term c plus v, which is the speed of light plus the speed of the frame. It may seem that the principle of the constancy of the speed of light is violated since we find in the bracket the speed c plus v. But in this example, we are measuring two events with synchronized clocks in one frame and non-synchronized clocks in another frame. In such condition we will find that the time is multiplied with the speed c plus v, or c minus v. If we transfer the speed of light from one reference to another, we will find that the speed of light is constant. In such transfer we imagine the following. A light emitted from point P'1 to point P'2 relative to K' at two different times, and a light emitted from point P1 to point P2 relative to K at two different times too. And when we apply the spacetime transformation we find out that the speed of light remain constant. So we are dealing with two non-synchronous events in two reference frames. We will see that in the next video.